Alright guys, so what these hypothesis tests are, it's kind of like using everything we've talked about this whole semester to actually analyze a claim that somebody's making. So this is sort of like what statistics is really used the most for. One of the classic places people think about statistics is with, for example, drug trials. Right? So if you're going to make a new drug and you think it's better than some old drug, you want to make a test, a control group that gets a placebo, those poor guys, and then you make a group that actually gets the real drug. Are you guys with me so far? Right? So if your claim is that your drug, let's make an example like this. Let's say we make a new drug. Well, it won't keep you up at night. Well, okay. So a new drug, and let's say that the old drug would get rid of your headache in like an average of, what do you got, Jeff? Like an average of 12 minutes with a standard deviation of, 4 minutes. Alright. That's the old drug. And we think our new drug is, obviously it gets, works quicker. This is the claim we're making. Okay. So it's a claim we're making about our new drug versus the old drug, be it Tylenol, be it whatever the heck your pain reliever of choice is. Right? How do I write this in Mathish, this claim that's being made? How do I write that from English into Mathish?
Mu less than 12?
Yeah. I think my mu for my new drug is going to be less than 12. I like it. So for right now, let's assume that this is going to be our standard deviation that we're going to use. So, if you were here last time, which one of these will this be? Yeah, it's going to be the high. Why is it going to be the high? These are my hypotheses. So this is really just summarizing what it is that we're testing out. There's always going to be kind of two positions to take. My position and the opposite position. Okay. So this guy, the null hypothesis, or affectionately known as the HO, has to have an equal sign. Because my rejection region, the area that's going to be enough evidence to show something's different, has to be not including the middle. It's got to be an extreme. It can't also include the middle, which would mean it can't have an equal sign. And we just decided that the high will always set up that rejection region. It's got to be one of the tails. So that's why this guy's always got to have no equal sign. So you put the claim in the place where it belongs. If it has an equal sign, you put it there. If it doesn't, you put it here. Now what goes here? Yeah, the opposite stance is it's at least 12. I like it. So if I can't find evidence that it's less than 12, then it looks like it's at least 12. Okay. So this one's my claim. Now the next step is kind of old news. This is step 1 out of a 5-step process. Thankfully it's not 8 steps like it was in my day. The second step is going to be, what the hell can you use to do this? So let's see, I haven't given us enough information. So to test this claim, let's say we test out our new drug on, what you got, Jeff? I don't know. 72 people. And we find an average of 10.9 minutes. So on the surface of it, that obviously 10.9 minutes is less than 12. But why is that not sufficient to just stop and say, well, there you go. It's less than 12. True, we got to take into account the standard deviation, but there's even a bigger point than that. Where'd that 10.9 come from? sample of 72 people. So there is a chance that I just happened to pick the people out that this drug works really well for. Because you guys have all been in a situation where your doctor gave you a drug and it didn't do shit for you, and then you say, oh, all right, try this one, and then that was good. If you haven't been, then you've had a lucky life. Because I've certainly been in that situation. This will work great. Didn't do anything for me, and then they said, try this. Oh, that was awesome. So we could have just happened to pick a bunch of people that it worked really well for. You guys kind of follow me. So the fact that it's only a sample that we've taken, that's why it's such extreme evidence that I have to show. It's got to be really far away from this number. In this case, it's got to be really far below that number. All right, maybe. But just because it's only a sample. So it's got to be a little more sufficient evidence. Before I get too far away from this step, how many tail tests is this going to be?
One.
Did you? I'm sorry, man.
Oh, one.
Second? Oh, one. Okay. Right, the import of your answer kind of get taken away from you, but I knew you had it. I could see it in your eyes. Second step is going to be Z or T scores. And you always have to tell me two things here. Don't just tell me one thing. There's two things. There's one thing that has to be true for me to do anything. And then the second thing is what determines if it's a T or a Z. So what's got to be true for me to do anything? Is it normal? Yeah. So is it normal?
Yes.
Yes. Normal. Why? I like it. Normal n is 72, which is bigger than 30. Central limit theorem says that looks good. And then is it Z scores or T scores? Z scores. Why?
Sigma given.
Yeah, Z scores. Sigma is known. So I haven't done a T-score test yet, but the only difference, if I had to use T-scores, I would just use the T-score chart instead of the Z-score. It's amazing. I would just use the T-score to set up what far enough away is. So again, this is what the hell I'm talking about. This is what I'm allowed to use to talk about it. Step 3 and 4 go together. Step 3 is going to be what's going to be enough evidence. How far away do I have to get enough evidence? Sort of like that thing with the coach. And to show me evidence that you belong on my team, you had to run this fast. Right? So this is going to be, step 3 is where we set up the rejection region. So again, at the heart of this, it should make a lot of sense. If somebody thinks the middle is at 12, and I just randomly take a sample and get something so far below 12, well then it can't be 12. The actual mean must be less. That's at the heart of a hypothesis test. Maybe. Alright, so I haven't given us information. What do I have to tell you for us to be able to do the rejection region that I haven't told you yet? Yeah, it's not really the confidence, but I understand why you said that. It's the little A fishy dude, alpha. So let's use, whenever we don't have alpha, we use 0.05. That's like our standard. So let's use 0.05. Let's try to be a 5. Let's try. Like most of my writing. So alpha is 0.05. This is a one-tail test. Why is it down here? Because I'm wanting something less than 12, so it's only that side that I'm interested in. Which again kind of enforces why the T-chart has a one-tail and a two-tail option. So I know it's going to be down there. I know I can use Z-scores. I know alpha is 0.05. So if you look at your T-chart, why would you look at your T-chart to get a freaking Z-score? Because it's on the bottom, and the T-chart is set up beautifully for hypothesis tests, right? Thank God I can use that. So 0.05, yes ma'am?
Why is alpha 0.05?
I made it 0.05.
Okay.
This has to be given to you. This is nothing that you calculate or something. This is the, like I was saying with the insurance company, they would make this alpha like 0.005. They want, really show me evidence that we should lower your bill. Or if I'm working in the nuclear power plant, I might make this 0.2. So I get off my ass the minute it's a little bit off kilter, right? So it all depends on the situation. That's why we have different levels of alpha. It depends on how bad it is to make a mistake. All right, I like it. I'd much rather go check the reactor every 5 minutes instead of just sit there and blow up. I think the first one is a better scenario. Do a little exercise and don't blow up. It's amazing. So who can tell me what the Z-score is going to be? Yeah, so you get your old T-chart. Z-scores are at the bottom. I got a one-tailed test, 0.05, so we go to the top row, 0.05. It's that second to last column. Go all the way down, I get 1.645. 1.645. Are you guys able to get that? Uh-oh. Anybody need a T-chart? I have some extras. Okay. Oh.
How did you know if there was one or two tails in? Okay.
Yeah, H1 is less than. I only care about, if I get up here, I'm not even going to do this. Like if this would have been 13, I'm like, oh shit, I'm not even going to do the test. It looks like I'm wrong already.
Okay.
So that's why it's only one tail. We only care about the ones that are down here far enough.
Okay.
I like it. When would it be two tail when H1 is not equal to?
Okay.
We're actually going to do one like that today. 1.645, but it's going to be negative. I really want to make that clear. The T-score chart obviously has no negatives on it because we're the humans. We have to know when it's on that side it's negative, when it's on the other side it's positive. Okay. So how do you say this in words? If the Z-score I calculate, so again, for the benefit of, well, everybody, but especially the people that weren't here, this is my benchmark. I've got to find a sample that is at least this far away. It's got to come into this little region down here. If I find a sample that is here, that is so far away from where I would expect it to show up if this was the real mean, that must not be the real mean. Let me say that again, because the idea is really simple. I know there's 5 steps. I know you got to calculate a bunch of shit. I know you got to worry about if it's Z or T. But the idea of it is remarkably simple. If I find a sample that is so far away, how far away? We define it on this step. That's far away enough. If I find a sample whose Z-score is down below this, then it is so far away from 12 that it can't be 12. The mean must be less. Because if the mean really was 12, where should I find a sample close to 12? Yeah.
So when you say you find a sample, you mean find a sample mean?
Yeah, take a sample, find a sample mean, see where it is related to the, when I get a Z-score.
Okay.
See where it is. So that Z star is the Z-score that I calculate from my sample. The reason I call it Z star is we have a Z-score here. This is what the book calls the critical Z-score. Shaw! Critical Z-score because that's the determiner between you showed evidence or you didn't show evidence, so they call it the critical Z-score. So I call it Z star just to set it apart from this guy. Z star is the one that we calculate from the sample. So if the thing I calculate from the sample is less than negative 1.645, what can we do? Come on, you should enjoy saying this. What can we do? If we find something in this region, and this region is called the rejection region. Reject the hole. Good. Which means if we can reject the null hypothesis, what does that also mean at the same time? We must be able, if we can say this guy looks wrong, we can say this guy looks like he's right. We can support the high. Alright, maybe. All kinds of dumb jokes I can make in there. I'll let you guys make them all yourself. Okay. So now, incredibly enough, we've set up what the hell we're talking about. We've set up what we're allowed to use to talk about it. We used that to set up what evidence is. What's going to be enough evidence. So now, obviously, the next step is freaking see where our sample fell. Did it fall here or did it fall over there? And then I can tell what the answer is going to be. So step 4. What's my... Oh, yes.
Can you explain again what Z star is? I mean, I get it, but I don't get it.
Z star is just the Z-score we're about to calculate.
Oh,
The only reason I put a star in it is so I can tell it apart from this guy, which is what we get from alpha.
Yep. So Z star is the critical Z Z-score.
Z is critical.
All right, all right.
Yeah. This is the one we're going to calculate right now.
All right, I'll stick with you.
All right. So what do we know from the sample? Yeah, N is 72. What else do we know? The mean is 10.9. We're assuming that we know sigma is 4. That's why we were allowed to use Z-scores. And before I make a Z-score out of this, what do I have to do? Always. Be careful how you say it. No. No. I want to go from that standard deviation to the one that works for groups of 72. I'm not changing it to a sample standard deviation. Yeah. That does not make it into a sample standard deviation. It just makes it into the standard deviation for all groups of size 72.
Is there a more succinct way of saying that?
Not really.
Okay.
Alright, so this is how far apart individual times are from the average time, right? So if I had a single person who it took 8 minutes for the headache to go away, would that be weird? No, it's 1 step away. Is that cool? That's old news. If I had a single person who took this drug, and it took them 8 minutes for the headache to go away, that would not be unusual. That's only 1 step down from the mean. Is that cool? No? Okay. This standard deviation is for when I take individuals. Right? So there is a distribution for this original drug. It might not even be normal, but let's pretend for a second it is. 12 minutes with the standard deviation of 4 minutes. That's for individuals. So every single person on this graph is a person. It's one person. There's individuals in there. So I'm seeing how spread out the individuals are. This poor person, it takes for freaking ever for that to work. Do you see that? It would take them maybe, 30-something minutes for that to work. This person, they go, oh, I'm better. It's like, holy crap. Right, maybe. So, this is one of the hardest things to understand, and I get this. It's really frustrating as a teacher to try to figure out how to say this, because it's nowhere near as difficult as it sounds. All right, Rev, thanks for that. So when I take samples of 72, by the way, if I said one person, it takes them 8 minutes, they're right there, right? That one person would be right there. Is that cool? What are all these other freaking people? There's other people, right? There are other individuals that I'm comparing that one person to. Does that make sense by itself? That's what we did when we first learned about Z-scores and Z-score charts and probabilities. We were saying the probability that this one person takes this long or something. That's what we were doing at first. Now, after I take samples of 72, well, for one thing, if I want to make it a little more, it's going to be a lot skinnier, right? Because if I take sample of 72, then the average of that sample is going to have to be a lot closer to the real mean. It's going to have to be. It's going to be really hard to get a bunch of people that just happen to get relief really fast. So that's the whole thing about the standard deviation getting smaller. But now I've got a group of 72 people. That's what I've got. I've got a group of 72 people. What do I want to compare that group to? Other groups of 72 people. That's the only way it makes sense. So each of these little dots now that make up this picture are groups of 72 people. So this is still a population standard deviation. It's a standard deviation for all groups of size 72. That's what this is. It's how spread out all groups of 72 are. This is not a sample standard deviation. It is the standard deviation for all sample means. All. Population. Still population standard deviation. Okay, maybe. Whew. It's one of the weirdest things to kind of get down. I understand this. Nuts and bolts wise, you can still do the work. But my God, I would love it if you understood the distinction there. What do you guys get here? Help me out. What's 4 divided by square root of 72? Do it again? 0.471. Okay. Oh, sounded weird. So now let's calculate Z star. How do I always calculate a Z-score? It's my data point. What's my data point? 10.9. That's the one that I got. What do we assume the mean to be? 12. Over this new standard deviation. 2 point something. Negative 234. So where did that fall in the picture? It made it, right? It's down here. This is one reason why I call it Z star, because you can put a little star. Oh. So our sample that we randomly selected, 72 people, we randomly selected 72 people, gave them this drug, and they fell way down here. If that mean is in the right place, there's only a 5% chance of this happening. So what's more likely is that mean is in the wrong place. My drug actually has a lower mean. Is this definitive absolute proof? Of course not. There's always a chance that we are wrong. And this is where people give up on statistics. But if you're hoping that math is magic and can tell you what lottery numbers to pick and can tell you exactly what to do in any situation, you're a little insane, right? This is life. This is real life. That's why I love stats. And stats is always like, it looks like this, but I could be wrong. I love that shit. That's the way it is. So what can we say here then? A little time. We can do what? We can do what? Reject the hope. Support the high. So how do I write this conclusion? Yeah, we have found sufficient evidence. I love it. Yeah, because which one was my claim again? H1, the high. So I can use this language. That's the other thing that students get really, they're like, what do I use? I don't know. No, it's never ambiguous. Whatever the claim was, if the claim was the ho, I would use the reject language. But the claim is the high, so I use the support language. Just all. Whichever one the claim was, that's the language I use. Why does it make sense? Because my conclusion should say something about the claim. That kind of makes sense. My conclusion should say, your claim looked right or your claim looked wrong. So we have found sufficient evidence to support the claim that what? That the new drug works faster. I like it. English gives you a lot of different ways to say that same damn thing, and as long as you've captured that idea, what's actually happening physically in the problem, I'm a happy person. Just don't say, we found evidence to support H1, yay. No, tell me what it is. Tell me physically what the hell that means. Last little piece. Is that still going? Yep, okay. How do I find the p-value? Well, we got freaking p-hats and p-values.
It's the area of the Z star.
I like it. Alpha is the area in the tail of the critical Z-score. The p-value is the area in the tail of my Z-score. That's it. So my Z-score is negative 2.34. So what area is in there? You can just look that up and find it, right? If you have the Z-score chart. I maybe have some extras if you need it. Yeah. So what do you guys get? I get 0096. I like it. So my p-value is 0.0096. That's what you would see in a journal article about a study. They would say p less than 0.01. And since it's such a small percentage, this is the actual probability that we just randomly found a sample where we did, if that was the real mean. So what's more likely? That, yeah, we just did something with 0.96% chance, or that this mean actually should be lower? What's more likely is the freaking mean should be lower. Does that make sense? I mean, that's the underlying idea here. Is we got so freaking far away from 12, how far away? That far away at least, that it looks like the mean actually should be lower. I like it, I like it, I like it. Can I say that the mean is actually 10.9? No, hell no. I can use this to show evidence that this number is wrong, but I can't prove that it equals this. You can never prove the mean equals something if you use a sample. Because the sample mean will almost never equal the real mean. So you can't use it that way. All right. There's a lot in there. Oh, shit. All right. So especially if you weren't here yesterday, you desperately want to group up with people that were here. I have calculators if you need to borrow. I have these, sir. But I will. I want you to work on, there's a front problem and there's a back problem. I want you to use both those.
Is that from the window?
Yes, as I say that, let me make sure. Yeah, there, and if it isn't, you use 0.05. Because in the book, I think they
I
sometimes
get
don't
the
use
difference between them.
good reason.
I think it's just confusing because he uses the word critical. Yeah. But like, if you think it's critical that whatever is in star values, it's critical that it has.